have special functionality. That is, placing data in them changes the operation of the microcontroller. So in order to do this, we need to know some values, some registers that are used inside this I/O. So one of the things that we use is actually the pins on the microcontrollers. So you see the small legs on the chip, these are called pins. And these pins, sometimes I can have some sensor and I want to read values from this sensor. So how can I communicate from the outside world with this microcontroller? I need to work with the I/O registers. So I have two instructions like LDS and SDS. I have in and out. So in is used for reading values from registers in the I/O part of the memory. And the way in works like this. So in RD, comma, A, where A is an address in the I/O field. So RD can be 0 and 31, so it's not limited like the LDI. And A is between 0 and 63. So if I look, before I said this is my GPR, this is my I/O. So here I have 32 registers and here I have 64 I/Os. So the way, so I can choose any I/O I want through the address here. So let's take an example. I can do something like in R2, 0x16. So does this work? Is 16 that, of course it is between 0 and 63. So it searches for the address which is 16 and read from it. Now here you might tell me, okay, what to wait. Here we go from 0x000 till 0x001f. So actually this 16 is relative to this location. So what A is a relative address. So we start counting from here, 0, and we go all the way to 63. Alright, so instead of using the real address, which is from 0x001f to 0x005f, we actually start counting from here, 0, 1, 2, 3, 4 until we reach 63. So 0x16 is somewhere between 0 and 63, and so my instruction works. 0x16 does not mean R16 in this case because I'm using with an N instruction. So, also instead of using addresses, I can use acronyms. So let's say I have two ports on my microcontroller, which is port A, port B, and port D. These are the pins here. So these are 8 pins. So this is port D and this is port B. I can use something like N R4 pin B, N R5 pin D. So what happens, it will take the values that are present on the port and place them in R4, and the values present on the port D in R5. So the difference now from the LDS and what we're doing before is that now we're actually communicating with the pins of the microcontroller. So if you see a chip and you want to connect a sensor, we want to read this temperature. So let's say I have a temperature sensor on port B. To read the temperature in a simplistic way, let's assuming it is digital and it gives 8 bits at a time, I read this value directly into R4 by doing in R4 pin B. Then once they are in the registers, I can do whatever I want. I can add them, I can store them in SRAM, I can do whatever I want with them. Elaborate more on the I/O part of the memory. We need to understand one thing, that is that there are two types of addressing. So assume this is the I/O memory, the basic I/O, not the extended one. As we know, this is the SRAM. Okay, so we have the GPR here, we have the I/O, and we have the SRAM. So this is actually the I/O, and if you remember, this is a 16-bit address. It goes from 0x000 till 0xFFF as maximum, and this part actually goes from 0x0020 to 0x005F. Now, so as I said, there are two types of addressing. There is the real address, which starts from 0x0020, and again there is the I/O address or the relative address, and there's the name of the register with specific functionality. So as I told you before, we start with 0x00 here. This is the relative address. And here we have the real address. Okay, so this is the address that actually is residing for this register. However, the I/O relative address will start from 0. We're gonna finish at 0x005F, and this will end at 0x3F, which is 63. Okay, now this register, for example, is called SREG, which we saw in previous lecture, which has all the carry flag and zero flags and all other ALU related flags. So this is a special type of registers. Again, we saw another register at 0x23, 0x0023, which is pin B, which has the input port of the microcontroller. Now, to do the transformation, we simply subtract 20 hex and we end up with 0x03. Okay, now if I want another one, let's say 25, 0x25, here it's going to be 0x05, and this will be actually port B, the output port of B. So to go to relative address, it's simply the real address minus 0x0020. So we can take any example from here. Let's take the last one. So let's say for SREG, the relative address is 0x005F minus 0x0020. It's going to be 0x003F. So of course there's a reason behind using two addresses. This is because the in instruction is only 16 bits and cannot handle these types of addresses. So this is why we use a relative address, so that we can account for all the bits here. Okay, so this is a small explanation about relative addressing and real addressing. Relative address is with respect to the first location in the I/O, and it goes for 64 registers for the I/O registers. Of course, this is the real address that actually can be used with LDS, and I'm going to explain this in a while. So the question is, can we use LDS to read from the I/O? Can we use LDS to read from I/O? The answer is yes. We can use LDS R5 0x 30, for example. So we know that 0x30 is actually residing somewhere here. So we can read from the I/O using LDS. However, N can be used also. So if I want to use this using N, I simply say RF, 0x0010. You notice these are the same. So LDS is reading from address 30. This is the real address. Of course, I made a mistake here. It should be 0x because I cannot use 16-bit address. So this is only should be 8 bits. So this is the real address, and this is the relative address, which is A in our description of N. So N R5 0x10 has the same effect as LDS R5 R30. So why do we use N instead of LDS? Well, it's the answer for this is for 2 reasons. LDS is 32 bits instruction. N is just 16-bit instruction. So actually N is smaller in size than LDS. Another reason is that, this is the first reason. The second reason is that LDS takes more cycles than N. So this means N is faster. So reduced in code size and a faster performance. So this is why we use N when dealing with IOs. And IOs are frequently existing in our program because they are our settings, they are our inputs and outputs, which dealing with the outside world. So this is why we need fast operation, and we need an operation that does not take so much time. Now, of course, as we have LDS and STS, we have also out instruction, which has similar operation than that of the STS instruction. So out instruction, so output data on IO registers. Of course, it uses relative addressing in the same way N uses. It has out A, which is the relative address, RR. And of course, the content of the GPR RR will go into the IO location A. So A is a number between 0 and 63. R index can be any GPR. So this is any GPR. And here, relative address. So now we can use something like LDI R15, 0x05. Here we read something from we place data into R15, and then I want to place it on port B. So actually I can put out port B. I can use its acronym, its name, and put R15. This will place 5. Another way of writing this one is actually giving the address. So if we noticed in this explanation of the I/O, port B is at 0x05. So what I can do is say out 0x05 R15. So please don't confuse this 5 with this 5 just by chance. It can be 6, 7, 8, but this is pointing to port B. So I can use this or this, but this is more readable. Actually, if I draw a small microcontroller like this, so here, and this is the Atmega 328. Let's say I have, this is port B, 1, 2, 3, 4, 5, 6, 7, 8. Of course, this is 8 bits, so I have the port B is 8 bits. So what happens is that I have 0, 0, 0, 0, 0, 1, 0, 1. So this is outputting to the outside world. This can be LEDs, so it's going to be all off, on, off, on, and I can actually control now anything that's connected to port B. So out is used for placing values, in is actually to getting values inside your microcontroller, such as reading some values from a sensor. Now, if you go and check other useful instructions that are available for us in the AVR instruction sheet, we have move instruction, move RD, RR, and it copies data between two registers. Of course, D and R can be between 0 and 31. So if I do something like move R10, R20, this means R10 is equal R20. And you notice that it can be confusing which is moving to which. You always remember that this is always the destination and this is the source. So always have this arrow going from right to left, which indicates that the values in R20 is now residing in R10. Another instruction that is useful is increment instruction, and it just takes one register, RD, and what it does, it increments RD by 1, and D of course can be between 0 and 31, which is any register in the GPR, and we can write it like this: RD is equal RD plus 1. A small example, for example, is LDI R16 0x00. So I place 0 inside R16, and then I do increment R16, and this makes R16 equal 1. So this is very useful in loops and other programs. Of course, as we have increment, we have decrement, which subtracts RD by 1. So I'm going to go over them really quickly. We have decrement RD, and what it does is RD is equal RD minus 1. So same effect, just decrementing the value. We also have subtract, takes two registers, RD, RR, and what subtract does is similar to add, but we do the subtract operation, which is RD is equal RD minus RR. So we subtracted. Of course, this is a 2's complement subtraction. So we'll check examples on later. If I want to do also some complementing, the comp instruction, let me just divide these. The complement instruction RD, what it does is says RD is equal RD bar. So here I just flip the bits. So we can say this is bit flipping. If it's 0, it will be 1. If it's 1, it will be go to 0. One final instruction before doing a simple program. It's going to be a jump instruction. So jump label. So this instruction jumps to a specific place in the program. For example, I can write, so a small example here, I can do something like LDI R16, 2, add, or let's use the increment R16, jump loop. So where is loop? I need to place somewhere where it jumps, so I put loop here. So what happens is I will read into R16 0x02, incremented by 1, and then jump again like this. So it's actually GMP, not J, GMP. So jump label. So I will do this over and over again until infinity. So this is an unconditional jump. It goes and repeat this program over and over again. So let us do a small program. Assume you have some LEDs on port B. So assume 8 LEDs are connected to port B. I want to write a program that toggles those LEDs. Write a program that toggles or flips those LEDs infinitely. So initially what we need to do is just imagine what's on the microcontroller. So we have these LEDs, all connected. Of course we have resistors, I didn't write them. So I want those to light on and off constantly. It's gonna be on means 0xFF, off means 0x00. So my code's gonna be, first I'm gonna start with placing some value inside R20. I chose it by random, above 16, and I will place 0x00. Then I want to place them on the port. So this is a special port. This is port B. This is a special register. It's not a general register. So I'm gonna use the out instruction here. Out port B. I don't have to memorize the address, and R20. So here what's happened is gonna turn port B off. The 0 is going into port B. Now I want to do something that's going for infinity. So now I have a loop. I'm gonna use the jump instruction. So I'm gonna write, this is the loop. I will say, how will I turn 0, 0 to FF? I can use the complement bit flipping instruction. So what I do is complement R20, which has 0 now. So now R20 has 0xFF, all on. Now I need to place them on the port. out port B, comma R20, here turn on, and then I'm gonna do it over and over again, jump loop. This will repeat forever. As you see, the second time I'm gonna complement R20, it's gonna have 0xFF, so it will flip to 0x00, and now I will turn off the port, and continuously doing this will be on off on off. Of course, this will be very fast if you test this program, because we need a delay to actually see the on-off conditioning happening on this microcontroller. We add delays. We're gonna explain this in later lectures. So we took as special registers, or I/O registers till now, I/O registers. We took pin B. It's used for input to port B. We have port B, it's output to port B. So if you're still confused, what port B is actually those little legs you find on a chip, on the microcontroller chip. This is port B. So port B is those pins there. So another register that we talked about is I/O register. It's called SREG, which is special register. And this SREG is called status register. And with this status register, what we do is, I'm gonna draw it. It has I, flag, T, H, S, V, N, Z, and carry. So we must remember that whenever we do a ALU operation, we have those 8 bits coming here, and the result. This is the result. So when we add two numbers, when we subtract two numbers, when we do any operation with the ALU, we have those flags that are connected to this SREG register. So what these flags mean? C means carry. So if you add two numbers and they are above 8 bits, we will have an carry overflow. So they will not fit the 8 bits overflow. Okay. And we have Z, the 0 bit, which means if result is 0, Z will be 1. So this will be 1 whenever we have a 0. This is very useful. We have the N bit, which is the negative bit. It's actually the most significant bit of the result. So if result is less than 0, D7, which is, if we take a look at this is D7, will be equal to 1, and this is the N bit in this case. What else do we have? We have also the V. So let's go ahead and check. The V bit is actually the overflow flag for signed numbers. So we have if A plus B is less than 0 and A is greater than 0 and B is greater than 0, then we have an overflow. Or if we have minus A minus B is greater than 0, then if these conditions are happening, implies we have an overflow. Now, if an overflow occurs, this means that the most significant bit is not an indication if number is a negative or a positive. So here we have the sign bit. So the sign bit indicates the real sign of the result. Okay, it's actually S is equal N XOR V. So this means if we add two positive numbers, so I'm going to give an example. So if we say A plus B and the result was less than 0, implies, how do we know this? This is because the most significant bit, D7, is equal to 1. So the result here is actually 1. However, we know for a fact that A plus B is are positive. So we also have, this is N. So we know for a fact that there is an overflow in this case. So V is equal to 1. Now, if I do an XOR between N and V, so the sign will be 1 XOR 1, it will give me a 0, which is that the number is positive. We'll demonstrate later about a real example with this. The last flag I'm going to discuss is the half carry. Here, when I have a carry between the two nibbles of the data, so assume this is, we are adding two numbers, this is 4-bit and this is 4-bit, so it's actually a carry from here to here. If you have a carry here, this is the half carry. This is 4-bit and this is 4-bit, so it's the carry on from D3 to D4. Okay, and if I write down, this is D3 and this is D4, so D3 is here. Okay, so now I'm gonna do some exercises about calculating those flags. I'm gonna do some short exercises. It's gonna be, let's say I have this program, LDI R16, 0x38, LDI R17, 0x2f, add R16 to R17. So here, if I ask the question, what is in SREG, i.e. what's C, Z, N, V, and H and S. So what are these values? So what we can do is just, we have 0x38 plus 0x2f. What we can do, we can change them to binary. Okay, and we have here 0, 0, 1, 0, 1, 1, 1, 1. So if I add those two numbers, so 1 plus 1, 1, 1, and here I have 0. So you notice that I have a carry of 1 here. This is the half carry. So I have here 1 plus 1, 0, 1, 1, 0. So the answer is, result is 0x67. Carry will be 0 since I don't have an overflow from this operation. Z will be 0 since result is not equal to 0. It's not negative. I don't have an overflow. Why don't I have? I added to a positive number and that number is positive, so there is no overflow. The half carry is equal to 1, and also the sign bit is equal 0 XOR V, N XOR V, which is going to be 0. Another example about calculating status register ALU flags is the addition of 0x9c and 0x64. So as with the previous example, we try to change the values of the constants used in LDI to binary. So we're gonna do this addition. So this is 1001, which is 9, and C is 100, and we have 6, and then we have 4. So when we do the addition, 0, we have a carry here, and then another carry. Remember, this is the half carry, and the carry ripples through the bits until I reach C, the carry out flag for the addition. So now if I want to represent the values of the status registers, I will start with C. It's going to be 1. The 0 bit is going to be 1 since result is 0. A common mistake here that you might think that the 0 bit is 0 because the result is 0. It rhymes, but no, it's not the case. It's if the result is 0, then the Z bit is equal to 1. The half carry is equal to 1, as we see here, the carry from D3 to D4. Then we have the negative is equal to 0, there is no overflow, and the sign bit is equal to 0. We'll discuss about NVS in later lectures when we have subtraction, and this is where these three will change and will have a meaning. However, we must notice here that this is an unsigned addition. So we represent 9C, it's a positive number, it's not actually a negative number, even though the most significant bit is actually 1, but here we're doing unsigned additions. So in the next lecture we're going to discuss more about this instruction and the representation in binary.